Okay, so we're going to look at basically an introduction to streamlines. And the way we're going to do this is we're going to look at a flow around some sort of sphere. So we've got a sphere here. It has a radius A. And we've got a flow around it. And you can imagine a particle at this point. If it comes up and it's moving in a straight line, it's going to kind of go around here like this. Another particle would go around here like this. And we're going to take a look at the streamline that starts here and ends right at this point at the sphere. Okay? So the problem states to consider the inviscid incompressible steady flow along a horizontal streamline AB. So AB in this case is this center one A, that's point A, and this is point B, in front of a sphere of radius A. From a more advanced theory of flow past a sphere, the fluid velocity along this streamline will be equal to V equals V naught times 1 plus A cubed over X cubed. So, and we're defining our coordinate system like this. Okay. Determine the pressure variation along the streamline from point A far in front of the sphere, that is, at A, we have that x of A is equal to minus infinity, so we're far away from the sphere, and the velocity at that point is equal to V naught, okay? To point B on the sphere, at that point, B, we can say that x of B is equal to minus A, and the velocity at B is equal to 0. We'll get into this a little bit more in the next problem, okay? So let's first of all look at some of the terms that I used. So the first one is inviscid. So an inviscid flow is one that has no viscosity. Viscosity adds a little bit of internal stress and strain, so we like to ignore it. This is actually completely unrealistic. All fluids have some level of viscosity, okay? But for the purposes of doing some of these problems, it's small enough that we don't need to worry about it, okay? Incompressible. Hopefully you're familiar with this term. But basically, if the flow is incompressible, that means that our density stays constant throughout the flow. Okay? A steady flow. This actually has a meaning. It's not necessarily that it's in a straight line, but the flow parameters, so things like speed, the direction, and the pressure, this is just some of the parameters that we could look at. They don't change for a given point. Okay, what this means is that I can pick any point in this flow. For instance, if I look right here, that point, the speed, direction, and pressure aren't going to change. Now, it may be different than the surrounding points or any other point I pick, but over time, those properties don't change for that point, okay? And then the last term I used was a streamline, okay? A streamline is a path that a particle of fluid follows. This is really similar to electromagnetic field lines that you probably ran into in physics. But the streamline in a steady flow has to, basically, a particle will follow a streamline in a steady flow. And any particle that is in that streamline at any point has to follow the streamline through, okay? So basically the streamline is kind of a constant for a particular flow, okay? All right, so the equation of motion along a streamline. So we're going to need that to solve this problem. By the way, once a particle is in a streamline or following a particular path in a steady flow, it cannot follow any other path. So it can't get out of that streamline. So that's kind of the idea behind it. All right, so I'm going to write a few terms out here. We've got minus gamma times the sine of theta minus dp ds is equal to rho times v times the partial of v with respect to s. Okay, so what do these terms mean? This is the term we use. So we're looking at the pressure along a streamline, and this term is basically what we use if we're looking at the streamline being tilted at an angle from the horizontal. Okay, so this tells us, so we've got our specific weight times the angle. So this basically is kind of a gravitational factor. So if streamline is tilted, okay, so basically that's going to tell us that that particle, and these particles may not necessarily be individual molecules. Maybe they're little pockets of fluid, if you want to think of it that way. If the streamline is tilted, that means it's going to be pushing the particle upward or downward, and that's going to change its gravitational energy. Okay. This term, of course, is the change of pressure with respect to the direction the streamline is going. So S here is kind of a generic term for the direction of the streamline. And P, so we're looking at the change in terms of a small amount of change in distance along the streamline. With respect to, that's what WRT means, direction the streamline is going. So if it's completely horizontal, that ds turns to an x. If it's completely vertical, that would turn to a y. Okay, and then this term, of course, is basically looking at the change in velocity relative to the streamline direction. Okay, so that's the equation that we're going to use to solve this. In this case, because we're looking at this streamline here from A to B, I'm going to change colors real quickly here. So we're looking at this particular streamline right here, right? Sorry. So we're looking at that particular streamline, and it's horizontal. So in this case, since it's horizontal, we're going to have the sine of theta, which is the sine of 0, and that's just going to be 0. Okay, so we don't have to worry about this term here. It's just going to go away. Okay, I'm going to move back to black here. Okay, so now the equation that we're going to end up using becomes minus the partial of the pressure. And since we're horizontal, we're going to change that S to an X is equal to the density of the fluid times the velocity times the change in velocity with respect to X. Okay. All right. So our velocity, we were given an expression for the velocity that is equal to V naught times 1 plus a cubed over x cubed. Okay, I like to write these out and multiply the terms out before I do the derivatives, just because it makes life a little easier. So we're going to have v naught plus v naught a cubed times x to the minus 3. Okay. All right, so the first thing is we're going to have to take a derivative of this with respect to x. So we're going to need d dx of v naught plus v naught a cubed x to the minus 3. Okay, so this term ends up becoming 0. And the derivative of x with respect to, or of x cubed, dx to the minus 3 with respect to x, ends up being minus 3 times x to the minus 4th. Okay, so dv dx, we will have minus 3 v naught a cubed over x to the 4th. Okay. All right, so let's plug this into our equation. So minus dp dx is equal to our density times our velocity, which we were given as v naught 1 minus a cubed over x cubed times minus 3 v naught a cubed over x to the 4th. Okay. We can probably simplify this out a little bit, so we can cancel these negatives here. So we're going to have 3 times rho times v naught squared times a cubed over x to the 4th times 1 minus a cubed over x cubed. Okay, so that's the equation that we're going to get for the change in density. If we want to look at it, we can kind of draw a coordinate system here where this is 0. Our sphere, for instance, would be right here. So this position is going to be minus a here. This will be minus 2a, minus 3a. And what we get is something that kind of at infinity is asymptotically approaching a 0. And then as it increases, it kind of comes up. And then right at this point, it goes to 0. So it looks something like that. Maybe I'll redraw that in kind of a red so it's easier to see. So it's going to go like this. It's going to peak and then drop down. And then after that, it's 0.